questions in tutorial 4. Okay, instead of waiting for the answer here, you can post it over there so that the other student can view it as well. And then I will check for you, okay, whether your answer is correct or not. Okay, so are you all ready for answering the questions? Okay, so I should move to the whiteboard right now, okay, by sharing the screen. Okay, so here I move to the whiteboard. All right. So questions 1, okay. Question 1 is radiant energy with an intensity of 700 watt per meter square strikes a flat plate normally. The absorptivity is twice the transmissivity and 2.9 times its reflectivity. Find out the radiant energy of absorption, transmission, and refraction in watt per meter square. Okay, so before I start answering these questions, I would like to see, is there any sharing in the Padlet? So far, no. Student, you can just click add over here. This time you can share your photo. Okay, share, you just capture your answer and then share it over here. Okay, you can just share it over here. All right, so I move back to the whiteboard over here. Okay. So this kind of questions is actually quite easy, students. You still remember we have the radiation property when there is a radiant energy strike on the surface. Okay, so you can draw the figure or draw the sketch the diagram, or you just can straight away do the calculation. So here is actually mentioned very clearly. Okay, the absorptivity is twice the transmissivity, and it is 2.9 times the reflectivity. Okay, all this term you should know. Okay, and I know that if the surface having absorptivity, transmissivity, and reflectivity, it will be a semi-transparent object. So it will be a semi-transparent object. So that's the incident radiation. Portion refracted. So some of the radiation absorbed, and then this is the transmissivity. Okay, so the question is asking you to find the radiant energy of the absorption, transmission, refraction, meaning that you need to find the refracted energy, okay, which is equals to reflectivity times the incident radiation, which is 700 in this case, and then transmitted energy and absorbed energy. Okay, and then for this case, semi-transparent object, we will have another correlation whereby absorptivity plus reflectivity plus transmissivity equals to 1. Okay, by having these two equations, I guess you will be able to find all these three. Okay? So you can start with any way, no problem. Okay, but I will start latest. Okay, so you will have the reflectivity equals to 2 transmissivity divided by 2.9. Okay, and then from here, okay, I can put it in this way. Okay, so, and then from here, plus equals to 1. Okay, so you just find one unknown first. I find the transmissivity first. Okay, it can be many way. It can be either way. You want to put all the unknowns in absorptivity also can. You want to find the reflectivity first also can, but here my case, I want to find the transmissivity first. Okay. So you will proceed. Okay, it is 3.69. And then you can get this. Okay, the transmissivity equals to 0.271. Okay, so I would see. Okay, are you all responding? I still couldn't see. Ah, yeah, I have some answer over here. Okay, let me check. I can remember this writing. I think this one is Benson, isn't it? Okay. You can see this one as well. Yeah, 0.27. Okay, the transmissivity. Okay, and then, okay, back here first. So that's the one. Okay, so yes, yeah, Benson start with calculating the absorptivity, and then transmissivity is 0.271. Okay, then 0.187 for the reflectivity, and then absorptivity 0.542. So the energy adsorb 379, correct? Energy reflected 130, correct? And then transmitted energy it's 189.7, correct? So this answer is correct. Okay. All right. So this answer is correct. So those students, you can compare your answers over here. Okay. For the rest of the student, then I will continue over here as well. So you can see either the whiteboard or the Padlet that share answers in the Padlet. Okay. And then here easily I can get the reflectivity equals to, then it is. And then finally the absorptivity will be 1 minus reflectivity, 1 minus transmissivity equals to 0.542. Okay. Then after that, if you want to calculate the energy adsorb, (379.4) energy transmitted and energy reflected. Okay. All right. So this one, in fact, is a direct calculation to let you all to understand the radiation properties. Okay. I back to the Padlet. See whether I have another post or not. So I just want to rotate it. Never mind later on. So that's answer 0.54. Yeah, correct as well. Okay, my students is quite shy to share your name over here. Yeah, correct. This answer is also correct. Okay. All right. Any question before we move to the uh the next questions? So this is questions 1. I can have the question 2 as well. For those who already answer question 2, okay, you can post it over here as well. Okay, so we're back here. I need to back to the PPP and see your answer. Okay, no response over here. Okay, so students, you can voice out. Okay, you can share your voice as well. You want to talk or you want to ask something. All right, because once I share my screen, I couldn't read your message over here. Okay, so I back to the whiteboard. So question 2 is over here. Okay, so the spectra emissivity function of an opaque surface. These questions you have to familiarize. So, okay, students, this kind of question, you have to be more familiarized because it will be dealing with checking the fractional value from table 12 2, whereby in the class I did mention that the most important part in chapter 12 is you have to familiarize yourself with the table 12.2, how to get the fraction volume and how to draw the figure and how to transform or deduce the information from the figure into the equation in order to get the answer or correct formulations. Okay, so the spectra emissivity function of an opaque surface at 1000 Kelvin is approximated as this one, this one. So it's given over here. Okay, so you have different emissivity value in different lambda range or wavelength range. Okay. Then after that, determine the average emissivity of the surface and the emissive power. Student, emissive power means that you have your answer in watt per meter square. Okay. If I don't mention watt per meter square over here, you should able to understand. Okay. Emissive power is watt per meter square. Okay. So I would like to check the here, the Padlet still haven't anyone want to share the answers over here? Okay, never mind. I go back to the whiteboard first. Okay, so you just draw the informations, okay, given. Okay, you can refer back to the questions. Okay, you have the emissivity value, and then here is the lambda. So there are three ranges over here. You have lambda 1 equals to 2, and then lambda 2 equals to 6. Okay, and then you have emissivity value for 0 to lambda 1, which is 2. Emissivity value 2, which is from lambda 1 to lambda 2, and from lambda 2 to infinity. Okay? I would say that this kind of sketching is not difficult to all of you. Okay, just transform the information given into the figure. Okay. So from here, you can easily deduce the equation. Okay, if you want to get the average emissivity, it will be okay from f 0 to lambda 1 plus okay from lambda 1 to lambda 2. Okay, maybe you want to put a bracket over here plus emissivity value from lambda 2 to infinity. Okay, and then you can further put it into the fractional value way. Okay, plus epsilon 2, and then fractional value at lambda 2 minus fractional value at lambda 1, and then plus epsilon 3, 1 minus fractional value lambda 2. Okay? So after this, you will be able to continue. Okay? So with the temperature here is 100,000. Don't forget from table 12 to you need to get the lambda T value. Okay, from here, lambda 1 is equals to 2, and then lambda 2 equals to 6. Okay, and then lambda 1t will be is 2000. Lambda 2t will be 6000. Okay, so the lambda t value is a good value. You no need to do any interpolation, extrapolation, no need. Okay, so you can directly read it from table 12.2. You may refer to table 12.2. Okay, so at lambda 1t, Okay, the F lambda 1 equals to 0.066728. Okay, at lambda 2t, you can refer to the table, to the lecture's notes. Okay. So after that, you can proceed with the substitutions already. Lambda 1 plus plus. So just do the calculations. It is equals to. And then after that, the emissive power will be, is a value from here times then you can get the value. The answer in watt per meter square. Okay, so students, you can proceed to the calculation. I need to check any posting over here. Couldn't see. Not sure whether I can rotate this one. Okay, so correct. The students, the answer. Correct. Okay. So you will get the average emissivity value of 0.58, or you can put it few decimal point. Then the emissive power is 32,608.67. Correct. Okay, your answer is correct. Okay. I couldn't see your name. Okay, so this is for question 2. Any more posting here for question 2? Any more posting over here, students, for question number 2? Only one. The rest are still calculating. Okay. So you will get this answer. Okay. Maybe some sharing answer over here. Okay. Scroll down. Okay. All right. Any questions, students? Oh, okay. In the Padlet. Thank you, students. Ah, all right. Okay, this is question 3. So this is question 2. Question 2. Wow, that's good. I received a lot of feedback. That's good. Okay, so okay, Ravin Raj. It's difficult to see. Okay. Yep, correct, Ravin Raj. Okay, then I will check for this students. Yes, correct. You can put it in your answer in kilowatt per meter square as well. So this one, yep, exactly, correct. Okay, Junti, maybe you can write your name over here, student, don't be shy. Yes, correct, Junti, your answer is correct for question 2. Okay, the students. Well, I'm very happy that mostly all of you have already done the tutorial questions. That's good. That's good. The important thing is you can, familiarize with the lectures learned and then the questions. Okay. So that's one. Wow. Okay. All right. Correct. Okay. So mostly get the correct answer. So I want to see these students as well. Question 1 and question 2. Yeah. Okay. Then I believe you can answer your uh, questions, assignment question. I guess it's assignment question number 2 or 3, part A. Okay. All right. Okay. So any more posting over here? Things in summary here. Okay. All right. So for question number 3, later I will be back later. Okay. So it's good you label over here, then we can differentiate which question. Okay. All right. So I move to question number 3. Okay, a furnace that has a 40 cm times 40 cm glass window can be considered to be a black body at 1200 Kelvin. If the transmissivity of the glass is 0.7 for radiation at wavelength less than 3 micron and 0 for radiation at wavelength greater than 3 micron, determine the radiation energy transmitted through the window. This one is actually also easy and similar with the question number 2. Just this one, it's asked you to find the energy. Okay, radiation energy means that your answer should be in watt rather than watt per meter square. It's not emissive power, but it's radiation energy. Okay, so I go to the whiteboard over here. Okay, so for this case, okay, I might need to check the Padlet as well over here. Question 3, where is question 3? Okay, yeah. So this is the correct way of drawing. Okay, you have the transmissivity. It's a function of lambda and t. Okay, it is 0.7 for wavelength less than 3, and it is 0 for wavelength more than 3. So as usual, you need to deduce your equations over here. Okay, you are not necessary to put T, but it's okay if you want to put T because it's a function of T. Okay, temperature. So you can continuously to form the second equation whereby you put it in a fraction volume equation, and then you will get 0.2825. Okay, of course you need to get the lambda 1t first. For refer to table, yes, exactly, correct. Okay, then you substitute in it, and then finally you will get the absorbed energy. Okay, so it will be better to put it in E absorb rather than Q. Okay, because this is not the rate of heat transfer. Okay, so for chapter 12, we will be using different terms compared to chapter 13, even though they are more or less the same, but this one usually we will put like E transmitted energy, ETR. Okay, but it's okay, it's correct as well. Okay. All right, can I get the other answer for question number 3? Yep, correct. Exactly. Yes, this one radiation energy transmitted. Okay, this is correct. All right. And then else, okay. Yes, correct. Students, yeah, you all, I guess that you all are quite familiarized with chapter 12 already because this chapter, in fact, it is not difficult. This one is all right. Then you need to state clearly, okay, where you get your f lambda 1 value. Okay, each of the step is very important. Okay, each of the step. All right. So any more question number 3 is over here. It's okay. So I need to check. Yeah, correct. 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 Just the things that you need to know. make it more specific or make it more detailed, like where you get this value, okay, from table 12 to some sort like that. Okay, if interpolation is needed, you have to show clearly, okay, the interpolation step. Okay, correct. All right, that's good. Okay, that's good. So shall we move to um, question number 4? Okay, students, shall we move to question number 4? Okay. So this one, I guess you all can refer to the answer in the Padlet. Okay, everyone can access, isn't it? Okay, you can refer to the answer. More or less, all the students are getting the correct answer. Okay, so any questions? Any question? I need to go back here. Okay, any questions? Do you all able to get the answers from the Padlet? For those who are still calculating, yeah, rather than I show it in the whiteboard. Okay, for those students who are still calculating, you can refer to the answer in the whiteboard, in the Padlet. Okay, so here you will get the answer. Okay, transmissivity 0.2825, and then eventually you get the energy transmitted is 5315. Okay, so the drawing will be like this. Then you have your lambda value. Here will be tau. Okay, so this is the drawing. Then you get these two value. All right. So if there's no questions, we will move to question number 4. Okay, students. So any more question? Any more posting over here? It's good that I can see your answer rather than I just show my answer over here. And then I found that you all you know, answer the question upfront before the tutorial class, right? Where I'm quite happy on that. At least you all, after the class, you all did some exercises. And in fact, if you try another exercises in the textbook or in any other reference book, you can show your answer to me. Okay, we can discuss. Okay, we can discuss on that. Okay. All right. So question actually for tutorial question 1, 2, 3 is basically under topics in chapter 12. Okay, for the fundamentals of thermal radiations. Okay, for question 4 to 6. Okay, for question 4 to 6 is under chapter 13. Okay, the radiation net rate of radiation between the surfaces, or radiation shield, or the radiation effects on the measurements of the thermometer or thermocouple. Okay, in fact, question 4 to 6 also quite easy. Okay, never mind, I will still share the answer here in the class. Okay, so before that, I would like to see the Padlet. Okay, question number 4 yet to be posted over here. Again, I back to the question tutorial 4, and then we go to the whiteboard. It's a long question, but actually it is not difficult. Okay. A 1.5 meter, this is question number 4. Internal diameter double wall spherical tank is used to store hot water and steam at 100 degrees C. The inner and outer wall are separated with the 2 cm thick space. The air between the two walls of the tank is evacuated in order to minimize the heat transfer. The surfaces surrounding the evacuated spaces are polished so that each surface has an emissivity of 0.09. The temperature of the outer wall of the tank is measured to be 30 degrees C. By assuming the conduction resistance of the wall are negligible, so no conduction happen here, and calculate the rate of radiation heat transfer from the hot water in the tank. So meaning that it's the heat radiation heat transfer between these two surfaces, hot water in the tank and also the outer wall surface of the tank. Okay, so the drawing will be like this. So the drawing will be like this. You have a spherical tank. Okay, there's a thickness over here. This is enclosed surfaces. Oh, my drawing is bad. Okay, never mind. I redraw again. Let it. I redraw again. Okay, so a spherical tank. Okay, so the thickness here is 2 cm space. Okay, so the diameter here is 1.5 centimeter, and the temperature inside is 100 degrees C. Outside the wall is T2 is 30 degrees C. Okay, both emissivity is the same 0.09 and outside emissivity is the same as well. Okay, so radiation transfer between two surfaces. Okay, you can refer to table 13.3. Okay, students, you can refer to table 13.3 and see, okay, what would be the correct equations over here. Okay, can you go to table 13.3? So I have this one. Okay, 13.3. Yeah, this is the one. Concentric spherical object. So you need to call out equation 13.40. Okay, 13.40. Okay, so it's a spherical tank. Okay, between the surfaces. Okay, so it's a heat transfer between the surfaces. It's an enclosed space. Okay, then you need to refer to these equations. So I call up over here, back here. So you write down the equation Q12 equals to okay. So what you need to get here is in fact you need to get the radius R1 and R2 before you can proceed. Okay, so R1 you can easily get it over here, 1.5 cm divided by 2. I think it's not cm, isn't it, students? Yeah, it's meter. Sorry, corrections over here. It's meter. Okay, so it is meter. 0.75 meter. Okay, so similarly, you need to calculate that mean R2, which is 0.75 meter plus 0.02 meter is 0.77 meter. Okay. After that, you can continue with the substitutions over here. A1 is a surface area of surface 1, whereby it's a tank itself. Okay, so you will have your 4 pi r square, students. For the spherical tank, you should know 4 pi r square. So don't forget your temperature must be in Kelvin. So outside temperature. Some students will make mistake over here where they put the temperature in degrees C, which is not correct. So you will get your answer in watt per. It's just in watts because the radiation between surface 1 2. Okay, it's time for me to go to the Padlet to see the answer for question number 4. There are a lot of questions, answers over here. Okay, I just make arrangement. Q3, Q3. Oh, I see question number 5 as well. So this is okay. Nicole here, question number 4. So we just look at the answer for the question for question number 6. I'm very happy, students. I see all this. All right, straightforward. Okay, you will get 211.6, correct? Okay, 211.6 watts. All right. And then I need to check Nicole. Yeah, correct. Nice drawing. Nice calculations. Nice start. Okay, good. Okay, next one. Yeah, correct. Correct. Okay. Maybe some of you would like to determine straight away the surface area first also can. Okay, good. Okay, that's good. Okay. So the answer is 211. Okay. For those who are still calculating, you all may refer to answers over here. Okay, everybody can access, isn't it? This Padlet. Hope it can help rather than I just one way sharing to all of you. But unless I can see everybody is calculating and answering the questions. Okay, correct. That's good. Okay. So question 4. All right. Any question before I move to question 6? Seems like most of you got the correct answer. I'm no worry on it. Okay. So any questions before I move to question number 5? Okay, you can start posting your answers over here for question number 5. Yeah, somebody is already, let me see whether the student put the name or not. No. Okay. So yeah, I move to question number 5. This answer is correct. Okay. Yeah, this answer is correct as well. Okay. So I go back to the whiteboard here, and then before that, I need to copy this one. Okay. Three infinite parallel planes, 1, 2, 3, having emissivity 0.2, 0.5, and 0.8 are arranged as shown in this figure. Plate 1 is maintained at 1200 Kelvin and plate 3, 300. Plate 2 do not receive any heat from external sources. Okay, what would be the temperature of plate 2? Okay, what would be the temperature of plate 2. Okay, so the assumption here is the surface area should be the same for these 3 plates. Okay, then I back to the whiteboard over here. Okay, you can start the drawing, or you transform the information to the sketching. So you have plate 1, 2, 3. Okay, so this is the information. Okay, students, you look. So here it's actually, you can see the heat transfer process will be Q21, okay, equals to Q23. It will be equally, okay, it will be equally transformed, okay, between the plates. And then here it's actually equals to Q1 to 2 and then Q2 to 3. Okay, the view factor rules apply over here. Okay, view factor rules apply over here. Okay, so when you have this kind of equations, so you can easily, okay, write down the equation for the parallel plates here. So this is the one, okay, for parallel plates, infinitely large parallel plates. Okay, then after that, you can substitute the answer or the values in it after you write down the equation. Okay, you can do the substitution in it, then you can get T2. Okay, here surface area, no need, okay, because it will be cancelled out. Okay, or you can do the assumption the surface area is 1 meter square, and eventually the surface area is not needed in the calculation. So by substitution, all the value in it, in fact, you can get T2, it's 69.2 Kelvin. Okay. The early concept is, okay, the plate is arranged in this way, and then you have to apply the view factor rules. Okay, Q21 equals to Q23, and in fact, it is equals to Q12 to Q13. Okay, eventually you will get the T2, it is X69.2. Okay, let me see the Padlet answer for question 5. Nice drawing here. Yeah. Okay. And then, so this kind of calculation also acceptable. Okay, you can get the 1Q2 first. Okay. 1Q3 first, then after that 1Q2 by using the shield equation. Yeah, just now I want to share as well. You can use the additional shield concept in order to get the T2. Okay, the rest of the student can refer to this sample calculations. Okay, either you can use the concept just now I show in the whiteboard, or you can use the radiation shield concept. Okay, it is correct. Okay, it is correct. Okay, so another question 5. Answer for question 5. So far, it's only one. Can I have the answer for question 5 from the other students here? All right. Yes, it's also using the shared approach. Okay, so it is acceptable as well. Okay, it is acceptable as well. So both um, calculation steps are fine. Okay, for question 5. Okay, good students. At least you all understand, and then you all have your own, um, solution step, and then at the end of the day, you get the same answer with mine. Okay, so at the end of the day, you will get the same answer with mine. Okay, so any questions? So we can move to the last questions, which is actually very easy, I would say. Okay. A thermocouple is used to measure the air temperature inside an electrically heated metallurgical furnace. The furnace of the thermocouple has an emissivity of 0.7 and a convection heat transfer coefficient of 20. The thermocouple indicates a temperature of 700 degrees C, and the true temperature of the air is only 650 degrees C. Estimate the temperature of the wall of the furnace. Okay, so this kind of questions is actually very straightforward and easy. In fact, you can refer to the slides. Okay, exactly this equation you will need to use. Okay, so the question is asking you to determine the temperature of the wall. Okay, by knowing the actual temperature of the fluid and then the temperature measured by the thermocouple or thermometer in this case. Okay, so you just need to have a quick drawing over here. Okay, whereby you will have the fluid and then the thermocouple. Okay, and then the temperature reading is 700 degrees C, and then the actual fluid temperature is 650 degrees C, emissivity 0.7, and then heat transfer coefficients. So a question is asking you to determine the wall temperature is how much. So straightforward, easy. Okay, so from here, TF given, TTH given, epsilon given. This is a constant, TTH given, H given. Just need to calculate TW for. TW, sorry. TW is what temperature, or you can put it in the Kelvin as well. Better to change all the temperature into the Kelvin. Okay, this is power of 4 as well. Okay, let me check the Padlet. See your answer. Q6. Yeah. So simple and straightforward over here. Wall temperature. Students, I guess that's the one you need to convert to the Kelvin. Okay. You double check your calculations and see. So this one must be in Kel. Oh, you change this one. Okay, I'm not sure. Okay, this one, this units is in Kelvin. Can you double check your answers and see? Okay, can I have the other? Yeah, that's the one. Yeah, you have to put your temperature in Kelvin. Okay, correct. Correct. About 980. Correct. Okay. Yes, correct, Benson. Okay. So the answer would be 980 Kelvin. Yes, Q6. Yes, we answered all the questions in tutorial 4 already. Okay. So, yeah, students, this one is free access. I guess you all can refer to the answer over here, okay, for the revision purpose, or you can jot down your answer. All the student got the correct answer. Very good. Very good. Okay. All right. So, if the is there any question? Any questions before we go for the break? For the tutorial questions? Wow, we finished all 6 questions in 1 hour. It's good. I think it's good to use the Padlet because I know some of you have done the calculation upfront. Okay, and then you all might need to just double check your answers is correct or not. Okay, so which is good. Okay, I'm quite happy on that, students. Okay, so if there's no question, shall we just have a 5 to 10 minutes break? Okay, so students, I have another one activity to all of you during this 5 to 10 minutes break. Okay, can you all just go to this one? Another Padlet, another Padlet. Okay, this link. Okay, so you just put one final question on this topic. So after that, we can back to the Padlet and see what kind of final question you want to ask before we move to discuss the assignment questions. Okay. So we right now go for 5 to 10 minutes break. Okay, if you have any question related to radiation, okay, just please post over the Padlet here. Okay, that's good. Students, start posting the questions. We can come back later on after the break. Okay. All right, students, we back to the class. Okay. Okay. Yeah. Let us look at the Padlet. One final questions over here. Okay. So, all right. I just want to share the screen. Okay. So, all right, students. Okay. Here, one, two, three, four, five questions over here, and I appreciate the students. Your answers is actually uh, 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 correct. Okay, and then your sharing here is acceptable as well. Okay, then we look at one by one. Okay, okay. Okay, for the Planck law in chapter 1, in chapter 12, the C1 and C is constant. Yes, in fact, you actually no need to remember all this constant value. Okay, it's actually to explain. So this equations, the Planck law is just to explain the situations only whereby you have a different temperature, different wavelength. Okay, this one the emissivity is I think 0.09 is the mentioned over there. Okay, for both side. Okay, can you double check? Okay, so this one Q5, if we are using formula for large parallel plate with shield 1Q3 with, yes, 1Q3 will be equals to 1Q2. Yes, this is correct. You just imagine you 1Q3 is without the shield. Okay, so the amount of radiation that emitted from plate 1 is will strike on plate 2. Okay, all right. So if you're using formula of large parallel ratio, yes, okay. If the plate are more than 2, can we straight away assume that the middle one act as shield? Yes, 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 this is yes. Okay, and then this is the students help me to answer yes, correct. The same concept. Yes, this is correct. Regarding on question 4, okay, so I think the same concept applies. Yes, correct. Yes, this explanation is good. Okay, this explanation for Q4 is also good. Okay. Okay, Ravin Raj, you have to check the radiation must come from the black body. Then the Kirchhoff law will be applied. Okay, the radiation source must be come from the black body. Okay, all right. Okay, since do not have more questions. In fact, if
Madam,
you
madam, madam.
yes, yes,
Sorry, madam. That one.
yeah, mm,
Um, Absorptivity and
mm.
emissivity.
Mm.
Those both will be same or will not be same.
Okay. Yeah, just now I answer. Okay. So both will be the same if the radiation sources come from the black body. So you have to check the questions. Okay. So you have to make sure
Okay,
if
madam.
before you apply this law, you will have to make sure the radiation is come from the black body. Okay. You can double check the
Without any
mm,
without any irritation, is it?
you can double check the slides, the definitions of the first line in the slide for this Kirchhoff law.
Okay.
Uh, okay. All
Uh,
right. Mm.
I want to double confirm. If there is initial radiation
Mm.
to that particular surface,
Okay.
that means the emissivity and the absorptivity will be different, right?
Yeah, if the radiation is not come from the black body source.
Okay, madam.
Okay.
Okay.
All right.
Thank you, madam.
Okay. Thank you. Okay. So I guess that's all for the one last questions posted over here. I hope you all enjoy the Padlet tools for today class. Okay, so any feedback you just let me know, or you do not prefer to have that, or you prefer to have like whiteboard showing all the steps. You can provide your feedback to me. Okay, as well. All right. So right now, I guess we have to move to the assignment question, isn't it, students? Yesterday I received some questions from you regarding on the assignment questions. Let me share the screen, share the question first. Okay, it's over here. Yeah. So these are the questions, 40 marks, submit before 5 p.m. in the ULearn platform. In fact, I already created the submissions folder. Okay. So for question number 1, okay, yeah, there are some try and error over here. Okay, try and error. I believe 1A you can explain. Okay, 1B, try and error is needed. Okay, you can start assume it is fully developed region first. Okay, then you can compare. Okay, so this one I believe all of you quite familiarized with answering whether it is fall under the this developing or not developing or fully developed region or not. Okay, you have to start with the thermal developing region. Okay, see whether it's fulfill the rate of heat transfer or not. Otherwise, you have to try the thermally fully developed region. Or you can start with, sorry, I think you need to start with fully developed region first because you have the constant Nusselt value, isn't it? Okay, sorry for that. I repeat once again. For part B, you have to start with assuming fully developed region first. Okay? Or either way will do. Because the reason I asked you to start with thermally fully developed region is because you have the constant Nusselt value. Okay? If you start with the thermally developing region, you have to assume, you need to have some assumption over there and then verify whether your assumption is correct or not. If it is not, then you have to repeat. So this is a 1 week assignment. 1 week assignment means that you still have time to get the correct answer. Okay? Not similar with like test quiz, you might need to stop over there and put your comment. No. Okay? No. Okay, you have to continue until you get the accurate answer. Correct one, acceptable one. Okay? So I hope that it is clear. All right? I hope that it is clear. Okay. And then for
Madam.
yes.
After we use the developed region, we will get a length, then we compare. After that,
Mm,
when we're finding the real length of the pipe,
mm.
that one, why we have to use the length we obtain from the thermally developed region for,
It's just an initial guess. You can assume any value, but thermally fully developed region, you will get the length, isn't it? But that one is
yeah.
just a guideline for you. Otherwise, you have nowhere to start with, isn't it?
Okay, I just
Uh,
wanna. This is just a curiosity, madam.
sure.
Okay, for our real life, when we're designing this kind of pipes,
Mm.
will they be doing like this? Like we assume first, then.
Yes, most properly. Yes, most
But
properly. Yes.
based on what I did is
Mm.
I'm very unsure. I'm not very sure that that is the length will be in the thermally developing region,
Mm-mm.
because at first we assume it is developed thermally fully developed region.
Yes.
Then we find the length. Then we compare with the thermally developing regions, the maximum length. Then the
Mm-mm.
assumption is wrong. Then when we want to calculate back the length of the developing region, I
Mm.
use back the length I assume
Mm-mm.
when it is the thermally developed region.
Mm-mm.
So it's all assumption. Will it be the
Yes.
correct one?
Um. After that, you have to verify whether your assumptions is correct or not, isn't it?
Yeah.
By calculating the L, okay, then you have to double check back, okay, whether it is falls under the thermally developing region or not, isn't
Yeah.
it? Mm.
Yeah. Sorry, madam. I just want to confirm.
Ah.
Okay, I already did.
Mm.
It's like I already understand the method, but why? Okay, I just explain that, madam.
Mm-mm. Mm-mm.
After we prove that it is a thermally developing region,
Mm-mm.
like after we compare with the length we obtain from the thermally developed region and we compare with the developing region,
Mm-mm.
Then we prove that it is a developing region.
Mm.
After we prove it is a developing region, when we're
Mm-mm.
calculating the real length of the pipe,
Mm-mm.
we use the length we obtain from
Mm-mm.
the thermally fully developed region. Why
Okay.
we taking that value? That is the question.
That is a question. Oh, why you taking the thermally fully developed region as a okay? Because you see, if the
Yeah.
land is thermally fully developed region, exceed this land, meaning that it's already thermally developed, fully developed, isn't it? That's
Yeah.
why you have to compare over here. If exceed this land, your assumption will not be valid again. You get what I mean? If
Mm.
if the line that you get, okay, is more than the thermally fully developed line, meaning that the flow already become fully developed region, then your assumption again not correct because you are assuming it is developing. It has to be
Oh,
less than
okay.
that, isn't it? It has to be
Yeah.
less than that. Yeah. Okay. So this kind of question is good because it's actually improve your thinking.
Okay.
Yeah, improve your
Thank you, madam.
understanding and thinking. You're welcome. Okay.
Okay.
Okay. Question number two. Okay. Similarly, you have to start with the estimations or assumptions, okay, of your TS value. Okay, this is nature convections. It's very obvious. Okay, so in fact, you have to continue your calculations as well. Okay, because this is assignment. Okay, assignments means that you have to continue your calculation to get the correct answer. Okay, so you have to get another new TS value. Okay, question number three, straightforward. No question on that, I believe. Since by looking at the solution that you posted in the Padlet, okay, I guess everybody can answer this two questions. Okay, okay, just in order to get the full mark, see, compare, students, discuss your answer, students. Okay, the key point is over there. That's why you have to complete your answer. Otherwise, you might not able to get the full mark. Then you will ask me why my answer is correct, why I couldn't get the full marks, because you did not answer the questions completely or incomplete answer. Okay, all right. So yeah. Any more question on the assignment, students? Any more questions on the assignment? Okay, Q3A, yes. Okay, Q3A. Okay, so you can look back your slides. The radiosity is reflected energy plus plus the emitted energy. So it is correct. E plus G reflected. Yes. Jundi, yes. You have to understand the concept of radiosity. It's clearly shown in the slides in chapter 13. Reflected plus emitted energy. Okay. So any more questions for assignments? Any more questions, students? Okay. How about the rest? How about the rest of the students? Hope that you all still with me. Okay. So if no questions, yeah, we have 30 minutes left over here. Okay. Um, I think we can discuss on the discuss on the maybe some um, topics for the upcoming test two, or you all want to end the class right now, then proceed to the revisions. There are two options over here. Okay, let me answer questions from Chinwei. If in the test, the question asks us to discuss, do we need to calculate the actual value? No need. Okay, in the test, no need. You just stop there and then comment and discuss your answer. For the test, no need. Okay, otherwise you will spending a lot of time. Okay, to get the real value. No need, no need. Okay, for the test, no need. For the assignment, because like you see, Chuan, it's actually 1 week. Okay, 1 week to complete all the questions, 3 questions, whereby you have sufficient time to repeat the calculations. Okay, for the test, no need. Okay, when you see discuss your answer and comment your answer, so no need. Okay, no need to repeat. No need to repeat. Okay. For the assignment, given a plenty of time to you, okay, you have to get it, okay, get the correct answer, okay. For the test, no need because it's only 1 to 2 hours time, no need. Okay. Yeah. Any more questions? Okay, students. Do you all want to end the class right now so that you all can proceed with the revision, or we can have some topic discussions over here for the topics that which will be covered in the test too?
Topic discussion, please.
Or topic discussion. Okay, topic discussion. Come, student, I want to hear your voice. So what topic you want to discuss regarding on the test? Yes. So which one, which topic that will you like to have more clarifications?
Madam,
Hmm.
madam, I have a question.
Yeah, sure.
Madam, as we learned just now, we
Mm.
already learned the forced external convection and forced internal convection.
Mm.
Okay. In industry, we combine these two concepts, right?
Mm. Yes.
So how? Okay. For now,
It's
we
not
only can
combined.
learn.
It depends. It depends. Because mostly the
Uh,
piping, we will more focus on the internal force convection. But it can happen depending on the surrounding situation. Okay, so the
um.
external is depends on the flow over the surfaces. Okay, the flow over the surfaces is depends on the environment. Whether the environment itself, you have like you are opening the aircon or any external means to force the flow of the air over the external surfaces. Okay, then it will happen simultaneously.
Okay.
Okay.
For example, madam, what if in the heat exchanger,
Mm-mm.
there'll be a flow is a counter flow, right? Inside
Uh-uh.
the pipe, there will be an internal force will be going
Uh-uh.
in right to the right hand side, and
Mm-mm.
external force convection will be going to the left hand side.
Mm. Yeah, heat
So it
exchanger is applied both because there is a
both. Okay.
exchange of heat between two fluids. Two fluids also flow into the heat exchanger with external means.
Okay. Then maybe we have to use both concept, right?
Yeah, both concept. But in the upcoming heat exchanger topics, usually you are focused on the overall heat transfer coefficient U value that I will explain to you I think next week we will start heat exchanger topic. And then in fact the U value is a combination of the internal heat transfer coefficient, the H value, okay, and external heat transfer coefficient, the H external.
Okay.
Okay.
Sorry, madam. Thank you, madam.
Okay, welcome. So after this, we will continue with the heat exchanger topic on next Monday. So after that, I believe you all can start with your integrated project designs already. Okay, so get all your groups ready and be aware of the date of submission, which will be on 13 August, isn't it, students? 13 August in one report. For me, you all no need to have any presentation. And then please check the rubric. The rubrics is the one that I use to evaluate your report. Okay, check the rubrics. Make sure you fulfill all the rubrics elements. Okay, otherwise it will affect your marks. Make sure all the members contribute. And then I believe based on Mr. Asri, there will be a C factor form for you all to fill in. Means that not necessarily you will get the same mark with your group members if you do not contribute. Okay. All right. So we come back here, the topics related to the test. Okay. Which one you want to discuss? Patricia, Nicole, Noraza, or I should refer back to the Padlet just now. You can post the questions over there if you are shy to talk here. Okay, you can post it in the Padlet just now. That one, the one final questions Padlet. Okay. Students. Okay. Percentage error, is it? You want to discuss about this one? Usually, I will accept plus and minus 5%. Okay. So in the test, if you have the terms like discuss and comment your answer, and then if you make any assumptions, okay, you have to verify on that, and then also give your comment, and also the percentage, okay, of your assumption accepted value will be 5 plus and minus 5%. Okay. So no questions? Get any questions over here?
Doctor,
Mm.
for the internal force convection for in tubes, for the TS, entry length, for laminar entry length is 0.5 RE times PR times D, right? 0.05 Reynolds number times Penton number times the diameter.
Internal force convection.
Yes.
Okay. Yeah. You mean the tubular?
TS for the
TS.
TS constant.
Okay, for TS constant. Okay. You meant about the Nusselt correlation or what?
Entry length.
Okay, the entry length. Okay, you have to use that one, LT laminar, isn't it?
Laminar.
Okay, wait. Okay, this one, isn't it? Can you see the slide?
Yes.
Can you all see that slide? Okay, you use equation 12. Use equation 12. Why? Because as I mentioned in the previous class, you see, this one is for thermal entrance region. So we have to use LT. In our textbook, we do not have the correlation if you are using LH. So you have to use LT.
Okay.
If you are using LH, it might be the other equations already. Okay, that doesn't if according to the textbook it's mentioned they don't have the the accurate Nusselt correlation to represent that. That's why we focus on LT over here.
Okay.
Okay.
It's basically the same for the QS constant, right?
No, this is only for TS constant.
Only for TS.
Yeah, only for TS constant.
And for QS constant, what are
We don't have.
the checking for entry length?
Yeah, you still remember there's a chart that I shown you all when you have the laminar, then you can refer back to that chart. Okay, in the revision.
I mean the checking for the entry length for
yeah, checking for the
QS
entry
constant.
length is only for TS.
For turbulent because laminar don't have.
For turbulence, okay, okay, both equation you can be used. Because usually turbulent, we do not have developing flow. It's all falls under fully developed turbulent flow because it started very fast. Usually the entry length for turbulent flow is very, very small, and it's usually once it's enter the tube, it's become fully developed for turbulent flow for most of the cases. Can you get what I mean?
Yeah, okay.
So
Doctor, can you brief us like the calculation steps that we have to go through for TS constant and QS constants?
Okay, sure. I need to.
Yeah, it's been a long time already.
Okay, okay, students. Another thing, I will try to. I guess the internal force convection video recording already available in the ULearn. You all can double check on it. Okay, in the video recording. Okay, on the internal force convection topics. Okay, for I guess no problem on the natural convections, isn't it?
No.
Okay,
Yeah.
because that one is quite straightforward. All right. Okay. So I go to the whiteboard. We just go through a very quick summary on the internal force convections. Okay. So you see, for internal force convection, you have QS constant. The first thing that you need to know is whether it is a QS constant or TS constant. It can be deduced from the question, or TS equals to constant. Okay, so after that, okay, you need to know the entry length. Okay, you need to know the entry length. Okay, and then after that, you need to know whether it is laminar or turbulent flow. Okay, so the entry length, you have LT and LH, and then for the for both the laminar and turbulent case. Okay, all right. So after this, you need to know, okay, if it is laminar, okay, you will have entry region or fully developed region. So bear in mind, this entry region is similar with developing region. They are the same, either. Okay, so after that, you have QS constant and TS constant, isn't it? Okay, so we don't have, okay, the equation for the QS constant. Okay, and TS constant we have, okay, the equation 8.62, and this one you need to check using equation 12 for the LT value, okay, which is 0.05 REPRD. Okay, so I believe you all will know that this is the length of the pipe. Okay, so let's say you get the you get the, let's say the length of the pipe is 100. And then you get LT equals to 0.1 meter, for example. And let's say it's fall under laminar. Then you get LT equals to 0.1. So means that 0.1 is developing. And then your length of the pipe is 100, so that this is become fully developed region already. This is how you categorize them into developing or fully developed region, because we have different colorations. Okay, and that's for the TS constant.
So
Alright.
doctor,
Yes.
sorry for interrupting.
Yeah. Okay, sure.
Because the first step we are checking the entry length, right?
Mm.
And which equation should we use? LT equals to 10D or 0.05 REPRND?
Okay, for this one, you need to check whether there's a QS constant or TS constant.
Yeah. And then the next step is entry length, right?
Yeah. Or either you can calculate the laminar or turbulent flow first. So you have to, if you are not able to calculate this step, okay, you need to check the laminar or turbulent first lah.
Oh, okay. So basically, I can do like
Either.
I check TS constant or QS constant first, and after that I check for the Raynaud number.
Yes.
Then I check which entry length that I should use.
Yes. So it will be more proper lah if you, because some of the students, they already familiarized with it. So it's okay. So you have to check the Reynolds number. It's the very first step. Of course, before that, the temperature that you need to refer to is the back mean temperature, isn't it? Ti plus Te divided by 2. Then you get the properties, and then you check the Reynolds number, whether it is laminar or turbulent.
Yeah.
And then maybe you need to check the entrance length over here, LT or L, the LT, or another one is what? Students? All of you cannot remember LH.
LH.
Tomorrow is the test, students. Okay, so after that, okay, you will need to proceed to Nusselt correlation, isn't it? So Nusselt correlation, you will back to here lah. Okay, see which case is applicable. Okay, so this is for fully developed. HD over K. For QS constant is 4.36. Okay, for TS constant is 3.66. This is for fully developed region. Okay, so this is the one. All right, if it is a turbulent, turbulent is very easy.
10D.
Okay. So you just use straight away equation 8.68. Okay, for QS constant and for TS constant. Okay, so usually we do not have the equation for developing region or entry region, and we only have for fully developed. Bear in mind that you need to check the N value is heating or cooling. So N equals to 0.4 for heating and 0.3 for cooling. So this is the one that you need to remember. Okay, so after you get the Nusselt value, then H value, then back to the Q. Okay, this is the flow. Extra step over here compared to the external force convection. Okay, the flow. Extra step, that's the one. Okay, this is the way to do the calculations. All right. Okay, so this is the heart of the internal force convection. So this, the entrance, the fully or developing region, the laminar flow Nusselt correlations and turbulent flow Nusselt correlation. Okay, so this is the heart of chapter 8. Okay, Any question? I believe you all know the correlation. You just refer to the slide. If it is QS constant, what will be the correlation that you need to use? The TS constant, what will be the correlation that you need to use, isn't it? So that one you can refer to the slide. Okay, previously we call it, you can refer to the appendix, but this time no need because it's all open book text or open book assignment. You can refer to any sources. But the time is limited now, students. It's only 1 hour, 30 minutes. Okay. And also the 15 minutes is for uploading. Okay. I hope this time you all are able to upload through YouLearn. Try do not send to email. Okay. I believe the time given this time is sufficient enough. Okay. 1.5 hours plus 15 minutes uploading the answer script. Okay. Okay. I want to see. Okay. Chapter 8. Chapter 13, what you need to know is actually the radiation shield. Okay. The way to identify the enclosed surfaces for different geometric in order to get the correct colorations. Okay, the initial part is just for chapter 13. The initial part is just the fundamental or the concept to derive all the equation in in table 13.3. Okay, so I go back here. Okay, let's share. Okay, chapter 13 here. Okay, the chapter 13, the initial sections is just some concept to derive the equations in table 13.3. So our syllabus, we will just focus on this kind of arrangement. We will not go further on this one. Of course, the radiation shield is important, the equation used, and we will just only focus in one plate, one shield. Okay, if you want to know more on multiple shield in order to further to reduce, okay, the radiation heat transfer process, you can you can read from the textbook. Okay, it has the topics over there. Okay, but we have limited time. We are not able to cover that sections. Okay, all right. We have 2 more important topics upcoming. Okay, heat exchanger and boiling and condensations. Okay, that 2 last topic. Okay. Okay, so I want to see the Padlet. Okay, only 1 questions here.
Excuse me, doctor.
Yes, sure.
So for tomorrow, the test, the duration actually is 1 hour and 30 minutes plus another 50 minutes,
Yes,
right?
exactly. Yes.
Oh, so it's like total is 1 hour 45 minutes.
No, you don't calculate in this way. That 50 minutes is for you to upload. Okay,
okay.
if you are able to upload within 5 minutes, I'm okay. So
Okay.
the total we can say is 1 hour 45 minutes. But I just worry some of the students might have a misunderstanding that you will have extra time to upload. No. So 1 hour 45 minutes is for you to complete all, including upload your answer.
Okay.
Okay.
Okay. Thank you, doctor.
Okay, welcome. So here the question, what is the difference between LT and LH? LT is you can look at the initial slides in chapter 8. LT is the thermally boundary developed profile, and LH is a hydrothermal, okay, whereby the velocity profile is developed. Okay. And then what else? There's no more questions over here. Okay.
Doctor,
Yes.
for internal force convection, we are not using LH, right?
Yeah, we are using LT, but for
Yeah, we're using
turbulent,
LT.
LT and LH is the same.
Yeah.
Mm.
And
Yeah.
for turbulent, LH and LT is equals to 10D,
10D,
right?
yes, correct.
Okay, thank you.
Okay, welcome.
Okay, doctor.
Yes.
Sorry.
Yes, sure.
For 10D, it means like
10 times diameter of the pipe.
yeah, for example, is 0.01.
Mm.
after you multiply, you got like LT is
0.1.
0.1. That means that beyond 0.1, the value all are turbulent, right?
Yes, all are developed, fully developed.
Oh, okay. All are fully developed. Sorry.
Yes. Yes.
Okay. So before the okay. All right. Thank you. And then for LT equals to laminar, right?
Mm. That one is for TS constant.
Okay. That one is for TS constant. And then after I calculate, for example, I get 0.1. That means that beyond that 0.1 is fully developed.
Yes. Yes. It's no
Ah,
longer
okay.
no
Thank you.
longer laminar already. You need to use the constant Nusselt correlation value.
So I have to use like NU equals 3.66.
Yes. If it is a
Okay.
TS constant. Mm.
All right.
Okay.
Thank you.
All right. So right now it's 9:55. Okay. So any more questions from the student? I can take one or two more questions over here.
Madam.
Yes, Raviraj.
Sorry, madam. Really sorry.
Sure, no problem. No problem. Yeah, just ask any questions. After this, you
Madam.
also can email me if you have any questions.
Okay, madam.
Mm.
I just want to ask for the concept.
Mm.
Black body means it will normally will release heat without
Emit.
any initial radiation.
Emit.
Emit. Emit
Emit radiations. Maximum.
without, even though we didn't give any source.
Yes.
Okay.
Yes.
That means black body don't need any irradiation for it to emit
Yes.
emissive power.
Yes.
Okay.
Yes. Mm.
Okay.
Okay.
Thank you, madam.
Welcome. So any more question? Maybe 2 or 3 more. You can still WhatsApp me. Okay. Okay. Diana is asking. We use LT for laminar instead of LH, right? Yes. This is for TS constant case. Yes. This is for TS constant case, Diana. So you will be using equation 812 lah. 8.12. Okay. Yes, Junti?
Excuse me, doctor.
Yeah, sure.
I want to ask if in chapter 8, if the surface temperature is lower than the inlet and outlet temperature, so the formula, the equation, can we alter it? The order is like the bigger values minus the smaller value,
Yes.
so we can get
Yes.
positive answer.
Yes. Yes.
Okay. Thank you, doctor.
Welcome.
Madam,
Yes.
for the same question as Junda asked, can we just proceed with the answer with negative?
You can, because it means that heat loss lah.
No problem, right, madam?
It is acceptable. It is acceptable because it's just
Okay,
the
madam.
final step that instead of gaining the heat, but sometimes you need to read the questions carefully. Okay, if it's asking you the heat transfer rate, it's okay. If it is asking how much heat loss from the pipe to the surrounding, for example, it has to be positive.
Okay. Yeah, madam.
Okay, I hope you understand
Thank you,
my question. Okay. Diana, when to use LH? So LH for this case, for laminar TS constant and QS constant, we are usually not using LH. Okay, we are not using LH for laminar case. For laminar case, okay. Seems like no questions for chapter 9, isn't it, students? And chapter 12 as well. Chapter 12, I already mentioned you have to focus on the table 12 too. So a lot of question for chapter 8, isn't it? So I would say that yes, over the years, the students will quite confused on internal force convection. Yeah, that's the main part on the I can say that the most difficult part in convection heat transfer topics. But once you understand the concept, okay, I would say that you will be able to answer questions as well. Okay, so it's almost 10 o'clock. Students, I can take one last questions. One last questions.
Doctor,
Yes.
the T lon,
Lock me?
not mean temperature, sorry.
Okay.
Mean temperature, can it be negative value?
Log mean temperature, somehow it can be. So it will become the cooling process.
No.
The
So-
heat loss.
Okay. So after that, when I substitute inside the Q, then it will be Q will be negative values.
Yes. It can be. Heat loss.
Okay.
Okay.
Thank you.
All right, welcome. So, okay, it's 10 o'clock. Don't worry if you are not managed to ask questions here. You can text me, WhatsApp, and also email me. Okay. So with that, I would like to end the section today. Okay. Before that, I wish you all good luck and all the best for the test tomorrow. Don't be panic. Okay. I believe 1 hour, 30 minutes plus another 15 minutes upload, it's sufficient to all of you compared to test one. We make improvement on this. Okay. We make improvement on this. Okay. So study hard. Okay. Don't take it for granted. As I mentioned, you have to start from the beginning, not during the test. Only you find your where is this section, where is that section, in which slide, in which chapter. No, please. Okay, the test duration is for you to answer the question. It's not for you to searching up and down the slides, the lectures notes. Okay, get ready your appendix table. Okay, don't be hair finding up and down. No, please, that time is not allow you to do so. Okay, be concentrate to answer all the questions. Okay, all right. Okay, with that, thank you very much, and all the best. Good luck in your test too. Okay, so yeah.
Thank you, Doctor.
Yes, I will meet you all on next Monday, and then we will start the new chapters.